Great afternoon, everyone. Thank you for coming. Today we have Matt Stock from the ANU. So Matt did his PhD at ANU on multicrystalline solar cells. He had a large part in the development of the slivers, and that's what I asked him to speak about. Sliver was such a promising technology, and it's very interesting to see how it's developed and what is the future. So Matt will present himself even better than me, so the first slide will be this one, so I will finish here. So please welcome Matt.
So thank you very much for inviting me. As you've said, what I'm looking at doing today is, rather than focusing on the technology, there'll be a bit in there, so those of you who don't know Sliver will have a bit of a sense of what it's about, but it's also about the journey that we went through. So the idea of taking a technology from the lab, from the first point of invention, right through to large-scale production. Unfortunately, it didn't continue, but we certainly got to that sort of end point. So in terms of looking at me, as you've said, I've did my PhD at the ANU. Originally started right back in 1993, so a bit more than 20 years I've been playing in the PV game now. And when that group started, there was 5 of us. So it was Professor Blakers and Klaus Weber was a PhD student then, and there was a couple of other of us who really were getting in there when the lab was first started. Shortly after that, I've spent 4 years doing a PhD in multicrystalline cells. So played around, was lucky that was involved with Andres Cuevas and Ron Sinton when they first started up the quasi-steady state PC measurement method, so I got to have a play around with that when it was first there. But as soon as I finished with that, I really got jack of multi. All this business of depending on who grows it and which day of the week it was, whether the material was the same, I decided really wanted to get back into single crystal silicon. So I was really lucky at that point that there was a project starting looking at single crystal silicon and trying to make very thin layers of single crystal silicon. Was the Epilift project. So I started in that, which migrated into Sliver. A couple of years into that project, the idea of Sliver was born, and then from 2003 through to 2013 I was involved in the cell R&D, and then ultimately was Chief Technologist for Sliver technology in Origin and then Transform Solar. And then when that wound up, I'm back again at the ANU. So where did this all start? So it all started with Epilift technology. So the interest very much during the late 90s was, how can we reduce the cost of silicon? How can we produce high quality silicon layers which are thin and lower cost than traditional multi and single crystal silicon? And the concept that we were working on was liquid phase epitaxy. So basically taking a metal melt, dissolve your silicon in that metal melt, you transfer that metal on top of your silicon, you cool the melt down, the silicon crystallizes out on the top surface of the silicon, we make our solar cell on that top layer, and then we remove that top layer and reuse the substrate. And that was the basic concept that was involved. And what you see down the bottom right is an example of a substrate that was grown, on this case a 111 silicon substrate. So what happens then is the silicon kind of wants to overgrow across the surface. So you can just have a few seed points on the surface, seed lines, and it can grow out and extend across the surface, have a few attachment points which are relatively weak, and we can just detach that layer. So the interest then is, why would somebody get involved in that technology right at the start? And it was a really interesting time in terms of energy, because there was a really interesting greenhouse. This was really the start of the greenhouse issue and companies starting to take it seriously. And Origin Energy, despite a lot of the very negative views that they're taking on solar in terms of the marketplace at the moment, were very focused on greenhouse because they saw themselves as being in a better position than most of the energy companies in Australia, because they were in gas rather than coal. So gas is a much lower greenhouse emitter, and therefore they were positioning themselves to be a greenhouse leader, and were really very heavily involved in driving government policy, etc. At that time. Origin is a growth company. They really aren't focused on being a revenue generator company. They're a company that grows. So they want to create new gas fields. They want to get out there and generate more electricity. They want to expand into international markets. It's all about growth. And therefore what they really saw was solar as being a potential growth vehicle. And this plot I'll come back to multiple times because it's a really important part of our technology story. But this is what it looked like coming into the year 2000. So the blue dots are cumulative PV installations. So as we've gone over time, starting right back in 1976, there's a few megawatts of PV had been installed around the world. And then over time, we're looking at the growth of the installations. And the thing that Origin was interested in was the spacing of those blue dots. And if you have a look over that period of time, PV was growing at 28% per annum. So the installations, basically the amount of peak manufacturing that was being done year on year, was growing by 30% year on year. And so this was the sort of business that Origin was very interested in getting into, something that's going to help them grow their business. There was a weak fit, it's energy, but they weren't really a manufacturing company. So what happened after that? Epilift progressed quite well. We were going through to 2000. And then the decision was really around how do we scale this thing up? So what we had there was a technology which required custom manufacturing tools, in that we had to design and build the tool which was going to take multiple wafers, insert them in this metal melt, grow our silicon, and then get them back out again reliably. And we had to be able to do this again and again and again, because there was only value in it if we could reuse that template multiple times. So Andrew and Klaus were coming on the train back from Glasgow, and they sort of were sitting there going, look, it's working, but is there a better way we can do this? And what they really focused on was, well, what's the cheapest way to make silicon? And the cheapest way to make silicon is the way that the solar industry does it. In terms of grams, cost dollars per kilogram, multicrystalline silicon and CZ silicon were the cheapest way to do it. So they started to think about what are the ways in which we might be able to use conventional silicon, but do it with a much thinner quantity of silicon in the final device. And this is what led to the birth of SLIVER technology. So what we do with SLIVER technology is we take a standard CZ wafer, except instead of being 150 microns to 200 microns thick as the solar industry is in today, we're taking something which is 1 to 2 millimeters thick, so quite a thick wafer. And then what we're doing is we're micromachining it. And what we're taking advantage of is silicon has this amazing property that in an alkaline etch, one of the crystal planes etches much, much more slowly than the other crystal planes. And we use it all the time for our standard solar cells. If we take a 100 silicon wafer, we etch it, we do the random texturing process. And what we're doing is we're creating these 111 planes all over the surface, which don't etch, in comparison to the 100 plane, the downward plane, which is etching. So what we've done with SLIVER technology is we've rotated our wafer on the side so those 111 planes are vertical. And so we can etch very, very deep grooves, which are 100 times deeper than they are wide. Okay? So if we can do that cutting at a very narrow pitch, something of the order of 100 microns or less, then we can get these strips of silicon forming within our wafer. And this is what we're interested in making solar cells with SLIVER. The idea was then to process the cells inside the wafer. So you do all your cell processing while all those strips are being held together. And then at the end of the process, we can take that cell, tip it on its side, and we get the big area increase that you achieve through this micromachining process. So kind of imagine it a bit like a deck of cards. You take a deck of cards, it's all nicely packed together, doesn't take up very much volume. Take them on their side and you spread them out, and suddenly you get this huge area increase. And that's what SLIVER is about. We're taking the silicon, slicing it up into these narrow plates, doing all the processing while they're held within the rest of the wafer frame, and then separating them out and spreading them out. So we're getting both silicon saving, and importantly, we're also getting a number of watts out of each wafer that we process. So this was all originally about reducing silicon usage. So the focus was very much on how can we get our grams per watt down. So this particular plot's in area, but another way of thinking about it is in grams per watt. The solar industry, when this was coming out, was looking at around about 7 to 10 grams per watt in terms of how much silicon was required in order to make a solar module. What we did when we were at the initial phases of this, we already had got things down to around about 2 grams per watt, and then by the end of the process we were getting down to less than 1 gram per watt. So it was all about originally focusing on silicon saving. The cell design also, because it was a very thin cell and it made out of single crystal silicon, it was very easy to make good cells. And we were naturally set up to have high voltage because we had a very, very thin cell. And it was also very easy to get very good surface passivation on the surface of our cells. Okay? We could do all of our processing in furnaces, LPCVD furnaces, oxidation furnaces, to get our processing down into the grooves of the wafers. Very good current. The cells are very, very thin, and we've got a collecting junction on both sides of the cells. So we have an emitter both on the top and on the bottom. So we only need 30, 40, 50 micron diffusion lengths to get the current from the centre of the cell out to our junction. So we get very good collection efficiency. It also enabled us to think differently about our module design. because we had a bifacial cell, we could actually try and use both sides of the cell. Because you can imagine when we take a cell out, it doesn't matter which way up the cell is. It's completely identical in terms of the processing. This is a truly perfectly bifacial cell. So if we wanted the highest efficiency, we could just pack all these cells as close together as possible and cover the entire surface of our module. But we could also save our silicon even further by spreading the cells out. So what we did particularly early on in the process was to actually take the cells and separate them and put a white rear reflector behind the cells. And that way the light that hit the rear reflector was reflected back onto the back side of the cell, and we could then recover some of the light. You don't recover all of the light though. So it's back into a trade-off situation. By spreading the cells out, so the red curve there is imagining the cell, spreading the cells out and reducing the amount of silicon. So as we spread the cells further and further apart, what we're getting is silicon saving, but the efficiency drops off much more slowly. So in terms of grams per watt, again, it's most beneficial to spread the cells out, is the best economics. So, a few years of playing around with that in the lab, we basically said goodbye to Epilift, threw it out, but kept all the milestones. So we took the exact same project and said, instead of doing this with Epilift, we're going to do it with SLIVER technology. And one of the reasons we could do that was that everything in terms of the cell processing was using standard equipment. It was 80s vintage standard semiconductor processing equipment. It wasn't solar processing, but it was standard semiconductor processing equipment. So using things like plating benches and using wet benches for micromachining and furnaces and all of those sorts of things. We didn't have to build new kit, which meant that we could very rapidly use the existing facilities to process this cell. Unlike Epilift, which really meant that we had to go out there and custom build these new tools. So we look along the experience curve a little bit further. Everything's behaving itself pretty well. What the red dotted curve is as an industry builds more and more of stuff, the general assumption is that we're going to get clever at building that stuff, and we're going to get better and better and more efficient. And there's this classic curve which is a experience curve. And what you tend to find with a lot of industries that if you take the log of the amount of stuff you make and versus the log of the price, you end up with something like a straight line. And solar, after the first few years of coming down, was behaving relatively well in terms of that curve. We did our modelling and had a look at what we believed we could achieve with SLIVER cells, and there was a really good fit. There should be a really good margin in this business if we can succeed. So Origin committed to building a pilot facility in Adelaide. So why Adelaide? Close to the researchers? Nah, not particularly. Good quality water. Everyone knows Adelaide water's top notch in an Australian context. No salts or anything else in that. Nice and easy to process. Lots of high-tech industry. Really good at making cars. It's pretty high-tech. Not really any of those reasons. And what I'll come back to is a theme that I'll come back to a few times. It's all about people. And in the end, the boss makes the decision. He wanted something that he could keep an eye on. So he wanted something that he could jump in the car and nip down and see, how are you guys going today? And that really was ultimately the decision why we were in Adelaide. We had a look at Melbourne, we had a look at Canberra, we had a look at Sydney, but the generation group, which is the part of Origin which was all about developing new business, was based in Adelaide. They came out of South Australian Gas, and that was where the energy part of Origin really started. And so that's where the head office was based. So that's where we ended up. And we started completely from scratch. Yeah, we did a search for sites and ended up with an old paint warehouse. The reason an old paint warehouse was great was it was bunded. They didn't want to have spills, they didn't want to find that something went wrong and went out into the countryside. So the entire warehouse was bunded, which was ideal for somebody who's doing chemical processing. So everything was going to be contained within this warehouse. And it was built completely from scratch. So what you can see there is, you can see the overall warehouse, and during the build, this is the assembly area, this is where the modules were made, and this is the clean room space within that. And this is then the yellow room for doing the photolithography during the build phase. So we progressed through that, and we had these two areas. We had the clean room area, which you can see, lovely fishbowl arrangement. It was all set out nicely with the window, so you can take the guests in and show what the monkeys are doing in the zoo. And then on the right-hand side, you've got the assembly area, which was pretty much just an office space, sort of class 10,000, 100,000 space for building modules. We weren't particularly worried about the cleanliness there anywhere near we were on the other side, which we were treating much more as a semiconductor processing space. And look, quite quickly we built the first modules. So the first part of things, we took things from the lab and threw them into manufacturing, and it came together remarkably quickly. The original product, the idea was not to certify, it was just to get a very limited number of modules out there, so and with some controlled buys, get a couple of 110 watt modules out into the market and just see what happens. Didn't keep going in terms of the plain sailing, and this is where we really ran into the challenge of guys who are in academia and used to being in the lab versus the reality of how do we make lots and lots of this product, and the thinking really is quite different. The first one which really we started to crunch into was defects, and particularly defects during the etching. So generally when we do processing, we don't care too much about one side of a wafer, okay? And a lot of the semiconductor processing equipment is very much focused on stuff going on the top side. In solar, we're a little bit more interested in both sides because we'll put a back surface field or some PERC contacts on the back, but pretty much the rear still is pretty robust. And what we found here was that both equipment and people handling things meant that we were actually getting a lot of damage on the rear of the wafer. So there were things that were associated with tools. This was one of the chucks on one of the tools. We're getting damage from vacuum wands where people were picking up the tools or with tweezers. Handling was another great one. People putting wafers in and out of cassettes. You slide it in and just nicely take the edge of one wafer and just drag it down the side of the other wafer, and you get these great scratches. You get these great scratches across the wafers. And of course we then stick them in KOH etching for a long period of time, and we take what looks like you can't see the scratch at all to suddenly it just blows out the entire wafer. We had a pretty poor cell design. We hadn't really thought through the issues. When we're building things in the lab, as long as some of them work, it's great. And we can sort through them and go, yep, enough of them work. Sometimes it does, sometimes it doesn't. And the biggest one that we got caught was we were trying to use one of our masking layers for multiple purposes. We would keep using it for both our etching process, and then we were trying to retain it later on to define where our contacts were going to go on. So we had this silicon nitride layer, which was on the top of our wafers. We were etching down between these grooves, and there was a bit of undercutting. It wasn't much, it was only 5 microns, 10 microns of undercutting, because we wanted these really deep, narrow grooves through our wafer. But we had then this uncontrolled breakage. These would come off and they'd land wherever they like. And so sometimes they would land nicely in the middle of the wafer and it didn't actually hurt anything. It didn't cause a problem. But some other times they interfered with the process. So this is a good example of it here on the left. We had this nitride flap sitting on the surface. We tried to do an oxidation to passivate the surface. The nitride blocks that oxidation. During some of the other processing, the nitride flap lifts off a little bit. There's no longer anything on the surface to passivate and protect the surface, and we get unwanted plating on those locations, which some of the time then also leads to shunting. So we started off with that sort of a problem. We also had a really bad module design. What I talked about before was the fact that we spread the cells apart and that we wanted to get light reflected from the rear. In order to do that as efficiently as possible, we wanted that reflector to be as far back as possible, because if it was too close to the cells, it was hard for the light to get sideways. Too much of the light was just going back out the same hole that it came in. So naturally, we went, well, we can just put that on glass. We'll put that separate from the cell. And to try and keep the weight down, we'll just put a thin layer of glass. We'll put a 1mm glass on the front surface. Of course, you can't toughen 1mm glass, it's too thin. So we can only use standard glass, but it's fine. We've got a 3mm glass on the rear. That's going to do all the strength work for us. But we quickly discovered, once we started to go into the reliability side of things, that actually this doesn't work. We find that that front glass layer stresses too much. Hail test is a total failure. The glass separates and fails on that test. And even the handling, in terms of the glass suppliers shipping them to us, we're finding a lot of product was getting broken simply in the transport of those materials. So the academic side of us, in terms of where we were at the ANU, was all about best performance, how can we get the best out of this, and it wasn't being driven by the manufacturability. And so there was a lot of having to rethink some of the approaches that we take to things in order to solve those sorts of problems. And great issues in terms of the rear reflector. The other side of thing, obviously, is automation. So while I talked about the cell process was pretty much a standard equipment, we didn't have to buy anything special. We could go to any second-hand equipment vendor. We didn't even have to buy a new kit. We could get old 150mm furnaces, old photolith gear, all the rest of it. That side of things was easy. As you'd be aware from the piece that's going around the room, what we've got is a lot of things we need to handle. Okay? We need to move large numbers of devices in order to build a module because we've got these very, very small cells. So how do we do that? Well, the first approach we went, well, it's automation. We're handling lots and lots of things. Automation companies, they're the guys to go to and throw dollars at the problem. Here's $1 million. Give us a machine that's going to take one of these wafers and make one of those modules that you got passed around. And in some ways that worked well. There was aspects of it that was good. So getting the cells out, they did really, really good job at. They were good at separating the cells from the wafer and getting them into place. Where things went pear-shaped was actually moving them around the place. Because what the automation companies, nobody has handled something which is 50 millimetres long, 1 millimetre wide, and 30 microns thick. They're springy. They want to bounce all over the place. You stress them wrong, they break. They've got electrostatics. If you put one of these things in a petri dish, it's just about impossible to get it off. All of these things are working against you in terms of actually handling these things. So while we could get them out of the wafer fine, the process of transferring them around, and you see a good example down the bottom here. This is supposed to be a nice little array of cells all ready to be transferred onto the module. And you see there's holes in the place and there's a cell going across in another direction. The automation idea, in terms of them being able to handle and actually move these things, they didn't know how to do it. And there was nothing they could do. It was just outside of the scope of what they're used to handling. So we had to go back to basics. It was something that we had to really just go, this is not something that we can do outside of house. We have to bring this back in-house and do this internally. So the approach then was go, well, let's not go for building $1 million machines. Let's go back to basic robotics. And so what we started off with was a basic SCARA robot. So a SCARA robot is your $10,000 robot. It's basically a pivot with an elbow on it. So it's something that can move around in one plane, and then there's a head on the end that can move up and down if you want to get your third dimension. They're a really cheap robot, very easy to program. There are hundreds of automation guys who would tune one of these things at the drop of the hat. And what we then had to focus on, how do we actually handle these cells? How do we separate it? How do we test it? How do we place it into the module? And what we did was we just slowed right down. So what we had to do was go for, let's go. So this is the sort of approach we had. Okay, very, very slow, methodical approach to taking the cells. So basically the head's going in, taking a single cell, passing it over light source, doing an electrical test, and then placing the cell onto a sub-assembly. So rather than building whole modules, what we built was sub-assembly. So what you passed around was a single sub-assembly. We're building those, and then we join those together to build modules. Okay. Surprisingly, even at this pace, because the robots are so cheap, the economics are okay. But it feels really, really clunky. It feels really, really slow. But the important thing there was all of the know-how that we developed was all around the head that interacted with the cells. How do we pick this cell up? How do we do an electrical test? How do we get it back onto the module so it ends up in the right place? Was all focused on the engineering just in that head of that robot. Okay? So I'm going to jump ahead in the story a little bit just because we're on automation, but we then went, great, we know how to do this, we've designed this head, we know how to handle the things, we know how to do it, let's go back to the automation companies and get them to do it faster. So they came back up with some great designs. We put 8 of these heads on a rotor and the sliver cells were feeding in here, and then we'd have electrical test here, and then they'd transfer it to a head here and all of the rest of it, and it all went to pot again. Okay. Once again, they just didn't have the idea of what things worked and what things didn't work, in terms of when things would break, when cells would go in the wrong place and all those sorts of things. So what we found again, we had to step back in-house. And ultimately, again, using standard off-the-shelf equipment. Okay, what this is a pick and place tool. So one of the tripod arrangement tools, and what you'll see here once that gets going. Okay, so what this is doing now, we've got 2 parts to the process. The orange robot on the far right is just grabbing a collection of sliver cells. There's an array of grids, taking out 20 at a time and plonking them on a conveyor belt. Vision system inspects them, rejects anything that has a scratch or is thin or has a defect or anything along those lines. So you'll see some cells are getting, it might be a bit hard to see, but some cells are getting passed through. And that head is very quickly picking up and aligning 24 cells at a time. So in that time that robot is going over there and grabbing off the white belt, it's picking up 24 individual cells. And it's adjusting for the position of every single one of them and then placing those across onto the one. So now we're getting into something which is starting to feel much more like the same sort of pace of build that you would have with a conventional large area cell operation. But it was a really interesting process to go through to discover that, hang on, the experts are actually not out there. There isn't actually anyone who's done this before, and we need to develop this expertise in-house. And it was the guys who learnt through all of those processes of what didn't work with the automation tools and what did work in-house, and learning those sorts of things, which really enabled us to get to the sort of tools that were suitable for large-scale manufacture. So over time, the next couple of years, the problem started to come under control. One of the things we do have to watch in that is that we probably damaged our confidence in our stakeholders a lot during that period of time, though. Because one of the things we did was we promised, yeah, we can do this. We showed all the upside, but we probably didn't communicate well enough the downside. Okay, so we didn't hit targets. We were still progressing well in terms of the potential to hit large-scale manufacture, but we started to put things in there that, hang on, do we actually believe these guys anymore? So there's an element of doubt starts to come in for people, because we started off before we built it, yep, $19 million, we're going to build this pilot facility, you're going to have 20 megawatts of production in 2 years' time. Easy. Actually, what we spent was 2 years troubleshooting a line and starting to get things going. Okay, so there are elements where you have to sell a business and say, describe the upside and all of these things and get people to buy in, but we do actually also have to go, hang on, do make sure that they know that there are downside risks, so that when they do hit them, they're not suddenly going, hang on, I don't know what's going on anymore and I don't have confidence in you in terms of delivering those. So we started to get really good production cells. We worked out a much better cell process that didn't incorporate those nitride overhangs. We incorporated a texturing process into the cell process, which is really important because we've got very, very thin cells. So we really needed that in terms of to get the efficiencies up. And so around the sort of 2005, 2006 period, we're starting to hit efficiencies around the 19% mark, which was enough to start to get people interested and opening their eyes to the potential of this technology. Particularly around that time, it's very high voltage for those cells, which also gave us the benefit of a very low temperature coefficient. We're quite robust to material quality. So what we started off with float zone material, because float zone material's easy. We started off with that at the ANU, and when we transitioned to the facility in Regency Park, we made the move from 4-inch to 6-inch because bigger wafers are more economic, in particular around the processing side of things. But we stuck with float zone to begin with. But then we managed to make the transition to CZ as well without having too big an impact. We also engineered the cells so that within the device itself there was a reverse breakdown protection. So by extending our emitter to meet the heavy doping under the base contact, we could form a tunnel junction at that the corners of our cells. So by doing that, as long as we can control that doping to a level, it didn't affect the forward bias performance of our cells. It was a tunnel junction that once we went about 5 volts in reverse, it would turn on. So that was really important for us in terms of the design of our module, because we had a very different module design. As we'll see in a moment, we build voltage and then connect cells in parallel. So it's very different to a conventional module, and we needed to ensure that if there were some strange current paths within our structure, that we could protect the cells. And what you could see here is as you push the cell into reverse bias, in this bottom left case here, we're pushing 3 times ISC and the cell's barely warmed up to sort of everything less than 40 degrees. And even if we sort of pumped 15 times the short circuit current of an individual cell, so imagining lots and lots of current being fed into one bank for some sort of defect or some other issue, temperatures were pretty controllable. And you could see the cell glow up as you increase the current. It would turn on at one point at something like 5.8 volts and then gradually at 5.9 volts. The next section would glow and then the 6 volts. You could control this along the cell and so spread the load of any heat being dissipated within the cells. So marketing love anything that says high performance and good and high efficiency and silicon and low reverse breakdown and perfectly bifacial. They're looking for all of those sorts of terminologies because marketing wants to differentiate your product from what else is out there. Okay? Particularly for a new technology like we were, everything was focused on trying to build SLIVER as a desirable product. The interesting thing with that is we also decided to go for a commodity product. Everything in terms of those cost curves was all about glass modules. But we had all of these things, bifacial cells, we had thin cells, we had flexible cells, we had the thing that is being passed around. But marketing always came back to the commodity product because it was easy. They could look at, here's this market curve, we can see the growth, we know we can sell everything we make. Okay? And so everything we focused on was focused on that commodity product. In terms of the module design, so what got passed around, what you see there is pretty much what we were producing in Boise at the end of the process. We had roughly 144 cells connected in series, and that was producing voltage as we connected the cells in series along these directions. And then the individual banks were connected then together in parallel. So however we then wanted to make a bigger module, we were taking these individual building blocks that you've seen passed around, and we just connect more and more of those in parallel. So we'd have a fixed voltage from whatever our subassembly was, and then we'd build that up in parallel. Let's skip through. And this then meant we could get onto some of the other things that marketing really wanted, and that was a demonstration of reliability. Okay? We had a product which was completely different to what everyone else had seen. Okay? So everyone looks at it and just goes, you've got thousands and thousands of connections, how can you possibly make that reliable? You've got 30 micron thick cells, how can you possibly make all that reliable? So again, we made the shift back to saying, okay, what are the things that we can control and take from what everyone else has learnt already? And so we really went back to a standard module design. 3mm front glass, EVA cells, EVA, Tedlar backsheet. Okay, we went back to all that because we know that's reliable. That's the thing that everyone knows works, and everyone's spent 30 years showing can last for 20, 25, 30 years in the field. And it all came down to then how do we build the building block for creating those. So the subassembly that was being passed, that was our core building block. If you turn it over, what you'll notice is that it doesn't look the same on both sides. One side it kind of looks like it's out of focus. So one side, what we've got is we've got fiberglass. There's crane glass is our substrate that we built all of our subassemblies on. So we're placing all these cells on this fiberglass shim, and that was okay because that fiberglass shim was actually being put in modules by people. People are having problems with cells cracking. We're putting that in there to avoid the thermal expansion inside the module. So it was actually helping control the expansion and contraction of the module. So with this new cell design, we could then, this new module design, we could push our reliability testing. So IEC standard testing involves thermal cycling from plus 85 degrees at 85% humidity back down to minus 40 degrees, and then up and down and up and down on a 6-hour cycle. So it takes quite a long time to get through a large number of cycles. You're probably talking 6 to 9 months of testing on here, but we could see that the modules could last very long distances in those, could handle the damp heat, so extended periods, 85% degrees, 85% humidity for very extended periods. We could demonstrate those sorts of things. So again, the sorts of things that get marketing happy. And then this is actually the second generation. Before that, we had already certified a first generation, so we could then go to certification. Once we were confident that the module's reliable, you then, in order to put a module onto the grid in anywhere around the world, what you need to have is certification. And that is somebody else has independently tested the module, both to say that it's reliable, to say that it performs to the standard that you say it does, and that it's safe. So those are really the three criteria that certification testing show. They don't guarantee those things because ultimately it's just a sampling, but in order to commit to that, the sort of cost and whatever else involved with that, you want to have confidence that you've got your processes under control. So once we had our reliability under control, we could then certify our various generations of modules. Marketing then want to say, so how does it perform compared to everyone else? Again, you need to be able to say, I'm at least as good at, if not better than the competition. So then you've got to do extended outdoor testing. So we basically set up at our Regency Park site. So this is our warehouse, the north-facing wall. There we set up a conventional sharp set of modules and tested them straight against SLIVER and just looking at results over the year. And again, positive news in terms of the marketing guys. We have got better energy yield than the standard one, and that's all about the high voltage. Okay, because we've got a high open circuit voltage, when things get hot, you lose less voltage than a lower voltage competitor will. And that's really where most of our gain was that we were getting much better voltage out of our modules on the very hot, bright, sunny day, which is really where you want your performance to be in terms of getting the most energy out of your system. The other one that marketing loved was partial shading. So one of the things about the sliver modules is that all of those banks were connected in parallel. Okay, so what we're doing there is we're adding the voltages of we're adding the current of all of those individual strips together, individual banks, rather than a series connection where all of the cells are connected in a single series string. Okay, by doing that meant we could pretty much shade any one bank or any part of one bank, and all you lose is that one bank. So if there's a leaf sitting across one of those banks on that one, we'd have had 6/7 of the power. If we covered two of them up, then we'd have 5/7 of the power. We didn't have any blocking of one bank talking to another bank. And marketing loved this. This was different, okay? And this is something that they really pushed in terms of Sliver to try and differentiate it as a product. But in the end, we're still selling into the glass commodity game. We're not developing anything that looks different. It's still a Me Too product. So again, all the things marketing loved, we had to chase after. The fact it was monocrystalline silicon, we didn't have to go through the thin film story. Silicon's reliable. Everyone understands that one. Demonstrating that things were reliable, that handling all of these contacts. Lots and lots of contacts was actually good in terms of us, because we actually had 3 contacts from every cell to every other cell. So if you have a look at the one passing around, because we're doing screen printing, doesn't matter whether we do 1, 2, 3, 5, however many, it's just an economics game. And for us, 3 was actually the best from an efficiency cost trade-off, which meant if any one failed, so what? 2 failed, so what? We actually had something that had some redundancy in there. So what happened during the next phase? So looking at the period through 2003 through 2008, we're starting to get our technology bedded down. People are starting to get confident that we can make these things. It's time to expand. Adelaide wasn't big enough. We really, the facility that we had there was never going to get us up to the large scale. And we're really looking at making the transition from 6-inch to 8-inch wafers, so from 150mm to 200mm wafers as in terms of our next phase. That was where the economics was looking a lot better. And it really didn't make sense to do this in Australia. We don't have a semiconductor industry. We don't have a really good support for high-tech manufacturing. We're a long way from the rest of the world. We're also going to have to ship everything around the rest of the world. So despite the fact that Origin was really passionate, and we were really passionate about wanting to do manufacturing in Australia, we never got to a point where that could work. The other thing that happened there, if you have a look at the red dots, suddenly the experience curve broke down. Okay, through that period, through to 2008, module prices didn't go backwards. Module prices stayed almost flat. The other thing that's happening there, the red dots are separating. Okay, they're getting further apart. Growth was accelerating. This amazing 30% growth that we'd had year on year suddenly was becoming 50% to 100% growth year on year. Okay, demand was accelerating, and that put pressure on silicon. Suddenly silicon was a constraint. Sliver, low silicon, woohoo! We're excited, this is great. Actually, it didn't work. And paradoxically, the silicon shortage really, really hurt us. Because nobody wanted to supply to us. Everyone's sitting there going, every bit of polysilicon I can get my hands on, I need to sell to the guys who are the big guys. We need to keep supplying them, because if we lose them, we're done. They're interested in the big volumes. We're using 1 gram per watt. So if we make a 100 megawatt plant, we're using 8 times less. Why do we want to sell you? We can sell more wafers to these guys. And we had a non-standard material. We had 110 silicon. Everyone else is in 100 silicon. So if we fall over, there's no one for them to sell it to. So going slightly off topic, the one that really got me about the silicon shortage was a trip to China that I had in 2007, I think. I went to one of our suppliers, and there were halls, I don't know, probably 1,000 people working in these halls. And they were all women, all Chinese women, sitting there sorting pieces of silicon. So little 1 square centimetre chunks of silicon. They were testing them, were they N-type or P-type? And they were just sorting all these pieces of silicon, because silicon was worth $400 a kilo. So broken wafers from the semiconductor industry were this huge thing. I visited exactly the same place in 2008. Same halls were empty. Not a person employed, because polysilicon supply had come on in China, and they were basically directed, you are going to use our polysilicon. And these thousands of people, see you later. That was the end of it. So silicon shortage was great because it was keeping the module price up, but it was really hard for us because we had to try and get somebody to believe in our product and believe that what they could get out of us, because we were willing to pay more for our wafers, was enough for them to take on that risk. Why partner? Origin, we didn't go it alone. Origin very deliberately tried to find partners, and we spent most of 2006, 2007 chasing down partners. And this was all about managing risk. Origin are an energy company. They're not a manufacturing company. Nobody had the feel for manufacturing. They couldn't look at a spreadsheet and go, yep, that makes sense. They couldn't look at a line and go, yeah, you guys are doing a good job, or you're not. They needed somebody else to say, hang on, this is okay. It's not that they weren't willing to take risks. They do it all the time. They build co-fired gas generation plants. Was a bit of a loss for them in terms of where things are at the moment. They're not being used, but they build oil and gas fields. They take big risks. They drill holes in the ground and hope. But they understand that. They know what the risks are. They've done it lots and lots of times. This was outside their scope. And it's the same, I think you get the same sense. Something you do every day, you go, yeah, that's fine. I can handle that risk. When it's something that's kind of outside that, you go, whoa, not so sure about that. And that's what we got caught with. So Origin wasn't willing to commit until we had somebody else on board. So we went through the search of semiconductor and solar companies and technology companies, and we went through probably 3 serious detailed negotiations. Took 6 months building up business plans, agreeing contracts, getting everything lined up, and everyone fell over on that final decision. When it went to the other company's board where they had to sign up the big checks, it all fell in a hole. And ultimately it came to that same risk. They're looking at it from the other side. They were all going, hang on, I've got my own business. I'm already a solar company. I know my supply chain. I can see my picture for the future. Yeah, silicon's constrained, but still I trust what we're doing. And everyone fell over. It was a huge investment. We spent 2 years probably with 3 different companies going through that journey of convincing them of the technology, understanding it, taking them through the journey, technology exchange, people going back and forth. But ultimately, people fell back to their own. So, plan B. Okay, we'll expand, we'll have a go at a small expansion, show that it works, and then bring the partner in to really get the business to grow. So we made the commitment. We had to go outside Australia, mostly because we wanted to take a brownfield site. So an old 200mm fab, and there are hundreds of these around the world. 300mm manufacturing is where all the Intels and the likes of those guys have got to. They've expanded to bigger wafers, and there are hundreds, well, probably 100, 200mm fabs around the world which are just sitting idle. Nobody can do anything with them because they just don't make economic sense for making DRAM or memory chips or whatever else. And they're cheap, cents in the dollar, 5-10 cents of the sort of capital costs that were originally invested in those. And serendipity hit. We were really lucky. We hit on Micron. So Micron in Boise, Idaho. What's his name? I've completely forgotten. Basically, there was a guy who was in potato chips, Idaho potatoes, Boise, Idaho, decided that he wanted to get into computer chips. So Micron was born as a company in the 80s in Boise, Idaho, middle of absolutely nowhere, and really huge in the memory industry. So you look at Intel, Samsung, and then Micron are your big 3 in DRAM and flash memory. And they'd just gone through the process of closing down their 200mm fabs. So they had a huge degree of very employable staff. They'd laid all these people off in the last year. They were interested in getting into solar because they'd seen all these experience curves, and they were in the memory game. Every year, costs come out 30%. 30% year on year you have to save in order to stay competitive in the memory game. So they wanted to get into something, and they've been looking at solar for a couple of years. So we knocked on the door, and they just went, woohoo, let's go. It took us 3 months to go from us knocking on the door to having a full-flown 50-50 joint venture running. Complete and utter serendipity. Went well for a while, but then that perfect storm hit again. So we've had gone from that period where silicon was in excess to suddenly there's a huge amount of silicon in the market, silicon component of the price went out, and the GFC hit. So that period of time where everyone's growing 50% year on year, 100% year on year, the demand wasn't there. So prices crashed. So we're at the point in 2011 going, do we go big or do we go home? And the decision was to go home. wasn't fundamentally a technology issue. We believe we could have been below that in terms of our cost position, but the risk was there and it was not clear where prices were going after that point. So we got hit. The dollars, geez, it was a big game for Origin. Between Origin and Micron, they sunk $240 million into trying to make Sliver a success. Original investment, $19 million in Adelaide, and then a final investment by the time we closed operations in Boise, $240 million. And you can sit there, some of those are paper losses, some of it you can write off against tax, and some of it you can write off against R&D, but it's a pretty big chunk of coin. ANU did pretty well out of it. I think it would be fair to say it really built a lot of the lab and a lot of the reputation for the ANU. There was more than 10 million in royalties flowed into the ANU, and 7 million I know of, but I think it was probably around closer to 12 to 14 of R&D projects that got driven through ANU through that period. So then it comes into some of the learning that came out of it, and I'm going to have to squeeze this stuff in reasonably quickly. One has to be really careful that how you look at making improvements in solar technology. And this is the model that I use. So I see there are sort of 4 core parts to making a solar technology work. You have to have the cost, you have to have it manufacturable, you have to have a good enough performance to be able to sell the stuff, and it has to be reliable. Those are the 4 pillars that I work, and they all interplay with each other. And you have to be really, really careful that you don't focus on one of those parts to the detriment of one of those other parts. And one of the great ones that we had to work on was increasing wafer utilisation. You remember those first wafers that you saw, there's kind of one rectangle down the middle of the thing. There's all this wasted space. Okay. So in order to do better, well, we need to pack more into that space, and we have to use a couple of cell lengths and start to do things around the different parts of it. So manufacturing scream, well, it's going to reduce yield, there's going to be higher stress, more wafers are going to break. You can imagine we've got this flexible wafer with all these stress points around it. Reliability, there's a 10% change in cell thickness, you need to recertify. We can't just do this independently. Our efficiency is going to go backwards. If we go for thinner cells, efficiency is going to go backwards. Okay, we need to have all of these chunks working together for the business to decide that these work. And no one can operate in isolation and just say, okay, I'm going to go full steam ahead. I know this is a huge cost saving. We need to take the rest of the organisation along on the journey. Goal alignment is really important. I'm coming back to this picture again. That little wall that was between our clean room and our assembly areas was quite amazing. There were just 2 independent teams with 2 completely different sets of goals for much of the time that we were operating. We'd talk in the lunchroom and all the rest of it. We were all considered ourselves, we were Origin Solar and then Transform, we were one group. But there was amazingly little interplay going from one side of that wall to the other. There were people who saw them as cell people, and I see myself as an assembly person. And a great example is trying to do yield improvement. The organisation cares about the thing over on the far left, total yield. That's what makes the business work. How much stuff can we get out at the end? So how do you do it? Well, wafer, you've got a wafer yield. You get as many wafers out as possible with as high a yield as you possibly get. Assembly, you get the highest yield. Every wafer you get your hands on, you turn into a sub-assembly. Module, how many sub-assemblies can you turn into final modules? How many of these fail? Feels like the right model. Everyone owns their own stuff. Everyone likes that one. You've got this nice wall. This is my stuff. I just operate in here. It's really, as long as I tick the boxes, I'm going to get rewarded. This is all good. And it just was a total disaster. Everyone upstream goes, I'm going to reduce the criteria. Scratches are okay. Few cells stucking together. That's fine. They'll deal with it. We'll just push that through. Completely opposite at the other stream. They're sitting there going, oh, we need absolutely the best product. We can't possibly tolerate anything that's got a slight blemish, scratch, defect, anything else. No, that's coming in the door. We're rejecting that. Okay. And there was this just total control culture of everyone upstream going, we need to push absolutely everything we can, versus the downstream saying we need to just reject everything that came, without any sense of how to compromise and merge these ones together. And it wasn't until we started to come back to, hang on, it's the big picture, it's what's good for the business, and try and drive those sorts of goals through in the behaviour, and that everyone shares those goals, that suddenly everyone's going, oh, hang on, this is important, this is the thing that we need to do. So we do have to be careful when we drive technology things that we don't set goals that drive bad behaviours. We had a really strange model. We kind of acted like a startup, and we kind of acted as big business, because we had Origin. So we had deep pockets. Money was never the limiting factor. We just had to convince our stakeholders that this was a good idea. It meant but it also meant that we were risk averse, because we had an organisation that was used to big structures. We analysed risk, we had risk matrices and charts, and everything was done to death before you made a move forward. And you'd eliminate one risk, and then you'd just go through the list, and then you'd have to eliminate the next one, and then the next one, and the next one. And that's really different to a startup philosophy, where you really are saying, look, is it good enough? Can we get to the next stage? Can we show enough to get the next funding round? So it's a very different mentality. And I think it really slowed us down, having this big company sitting behind us, but sitting isolated as a startup. The positive, we had a really strong team ethos. Okay, everyone was pulling in the same direction. We had a common set of goals once we worked out where the walls sat. Us against the world. We wanted Sliver technology to work. And the plus also of having Origin there was, it was a door opener. We were a big company, and therefore people would open the door and say, okay, I can see you're a multi-billion-dollar company, I'm willing to talk to you, rather than being a startup and them going, are you really going to be there in 12 months' time? The other one was, don't underestimate the need for a champion. We were really lucky that we had Grant King, who's the CEO of Origin, and the head of the generation department, Andrew Stock. We're both passionate about solar and passionate about Sliver succeeding. And it was them who really managed to keep the organisation going. This is something worth chasing after and worth investing in. And keeping them on side and keeping them understanding where things were at and keeping things progressing was really important, because you need somebody who's going to go out there and fight for the cash. Whether you're a startup or whether you're a big business, you need somebody who's got enough clout to say, this is important and this is worth chasing after, and to be willing to fight for it. So, biggest satisfaction? Look, there's no question that solving the technical problems was great fun. I'm a problem solver. That's what I enjoy doing. I love seeing, here's something that I don't understand, or here's something that needs to be solved, or whatever else. The micro machine that we did was better than anything anyone had done anywhere in the world. We were getting amazing etch ratios. We're etching through 1.5mm wafers with 10 microns of kerf lateral etching. There's these amazing structures. We got to 190 watts of power out of a single wafer that we processed. It's just huge. I mean, you talk 4 watts for a standard wafer. We were at 190 watts. So we could afford to spend money on these things. It was a lot more complicated, but it was there. We were simplifying the cell process. The SDP journey was fun. But the other part of it is building good teams. I had to go through this journey 3 times for this one. We built the ANU fab, we built the Origin pilot plant, and then we had to build the teams in Boise. And one of the things I've learned here is I've changed from being a task person to much more understanding people. It's not a journey I would have thought I'd been on 10 years ago, but recognising that what motivates you versus what motivates you versus what motivates you, I need to understand if I want you to do something. A people person is great if you've got to do something across 2 teams. Getting them to engage with the other team and saying, this is our problem, can you help us solve it? Pulling those sorts of things. The problem, which is really isolated, the task person, getting them into it and saying this is something that they get their teeth in, and understanding how to allocate those sorts of things to make it work well is something that I'm very different about compared to where I was 10 years ago. And you get to be a fashion model every now and then too, in terms of trying to market your material. Biggest disappointment, the focus on the commodity product. In hindsight, it was a real mistake. It was great when the business looked good, when everything sat on the experience curve, but as soon as things went pear-shaped, we didn't have a plan B. We didn't build products which benefited from Sliver. And probably this is the one, a roofing product, a lightweight, flexible, like what you were handling around. Everyone loved that, but it was really hard to get marketing engagement in that. Commodity product is easy. Everything, I can just see the market. Here's the price, here's the spot price. I can sell at that price. That's all I have to do for marketing. This was a new product, and it was really hard to get sales and marketing engaged in. So how many of these can we sell? What's the market scale? What's the premium? Putting these things on roofs that you just can't put a glass module on was really hard, and the benefits were just recognised too late, and probably maybe could have been the saviour of the technology. So that's it from me. That's my technology journey. Sorry, I've kind of gone off time and left not a lot of time for questions. We're going to go for lunch, so if anyone does want to come along and have a chat or has got any questions, or if you want to grab, have we got a couple of minutes or?
It seems so. We don't see the other class.
Okay.
So let's thank Matt. It's great work. Any questions? Everyone notice Hannah, this handsome guy in the... Matt, can you put the...
Indeed.
But everyone will sit with white shirt and more questions? Except of who is Annie?
Yep.
Matt, if you've got a product that you can sell, it seems to me that like a lot of the OPV stuff, you've got to find a product that you can sell your technology into rather than trying to compete on the power module market.
Yep, and that's really the last that last slide. It's saying exactly that. If we were in sliver manufacturing, there are hundreds of people who just are nuts about the cells. Okay, there are people who are interested in bifacial. There are people interested in flexible. There are people interested in concentrators. There are people in consumer electronics. Our problem is not really those markets. It's getting enough of those together to justify cell manufacturing, because cell manufacturing requires an investment and requires a commitment, and which is completely different to what everyone else has done. And that's really the hurdle we've got at the moment, is getting somebody passionate again about one of these concepts enough, and that they can see a big enough market that they can pull it. So either we've got to get a consortium of those together, and they between them go, I want some of these and I want some of these, and these together, there's enough for them to say, let's invest in some sliver manufacturing. But it's the cell manufacturing that's the killer. That you need to have cells in order to have product, and you can't have cells unless you have product. So there's this chicken and egg until we get somebody who's, I think, really passionate about a product, or a consortium of people who are passionate about products that pull the manufacturing again. That's our challenge now, and I think it's not clear that how we're going to get to that.
So who owns the IP?
It's all back at ANU, so it's all ours. Otherwise I probably wouldn't be allowed to give the talk that I gave today. There's a lot of information in there that if it was still sitting with somebody else might prefer not to be in the public domain. But it's now an ANU product. There are some people that we're talking to, but look, I'm not sitting there going, I think in 5 years' time I'm going to be back in sliver manufacturing. I think I think if we had the lightweight product a year earlier, and that's all we probably missed out on, they were ready to certify, and I think we'd have had a market there, but we weren't at the point of closing down saying, yes, we know we can sell 200 megawatts of this product a year at price X. We just didn't have that confidence.
How big is the flexible module market today? Like, is it big enough to justify the kind of manufacturing that you needed then?
The biggest, the most successful company in a lightweight product was Electron Devices. Who were they? Did the amorphous silicon. So they had a 5%, 6% efficient rollout module product. And I think they hit up to about 200 megawatts a year of sales. So
Unisolar?
Yeah.
One of those.
Is it Unisolar?
yeah, Unisolar, that's exactly. So the market was there. There was clearly an interest. A lot of roofing companies are very interested in it as a value-add product, particularly in countries like the US where shingle roofing is quite large. So in Australia, you're replacing tiles versus replacing ColourBond. It doesn't necessarily have the same fit, but a lot of the lightweight roofing, so warehouse roofing, they just couldn't take the weight. You can wave your hands and say it's a huge market, but it's not a market that you can go and point to and say, and there's where people are producing it. SIGS is really interested in that space, so that's really where I think SIGS is trying to get a foothold. They haven't hit a cost point where they compete with the crystalline silicon yet, and so that's where quite a few of those companies are trying to position themselves, but nobody's really hit the sort of volumes where you'd say, yeah, I have confidence that market exists. Yep.
So everyone seems to think bifaciality is great and the next thing to go for, but it never seems to quite happen. I mean, there doesn't seem to be even a standard for how to test, like IV test bifacial cells.
Yep.
So what's the big stumbling block?
Application. I mean, it's an interesting time in the US at the moment. For some reason, bifacial seems to have an extra presence. There are artificial markets being created around those. Beyond that, you've got to believe that putting them up as highway barriers where it doesn't matter what orientation. The beauty of bifacial is a vertically oriented bifacial has an almost perfect response. It averages out very well during the day, and the exact orientation is not critical. So it's an interesting space, but nobody's really managed to crack it. So I would say things like highway barriers and those sorts of things where you want to orient something vertically, a bifacial module sits really, really well. Beyond that, it's hard to justify, I think.
Thanks, Mark, again for the thing that you
Sorry.